In this lecture we talk about divisors on curves. So say you have a curve like this C, and this is embedded in some projective space. So now you pick up some points on the curve. So say you have this point P1, you have point P2, then you pick another point, say P3. There are infinitely many points on the curve. You just picked up 3 points. And to every point you attach some integer. So let us attach 2 here, 3 here, say minus 5 here. So you get a divisor. So this divisor D1 is 2P1 plus 3P2 minus 5P3. And what you have done to the other points, you've just attached 0 to other points. So now you can have, say, another divisor. Say another divisor D2 is, say, 1 times P1 plus P4. So P4 is some other point right here. But now you can add these two divisors. You can have D1 plus D2. That you just add coordinate wise. So you get 3P1 plus 3P2 minus 5P3 plus P4. Because these points P2 and P3 are also here. They are just 0 times P2 minus 0 times P3 or plus 0 times P3, and this P4 is here. So you can do coordinate wise addition. So this forms a group. Now more formally, the divisor on a curve is like this. Points lie on the curve. Every point you attach an integer. And this is a finite sum because most of these points have 0 attached to them. So except for a finite number of points, you have NP0. Now you can talk about the degree of the divisor. That is, you just add up all these integers. So the degree of D1 is 0. 2 plus 3 minus 5 is 0. Degree of D2, 1 plus 1, if this is degree, is 2. So degree of D2 is 2. Everything else is 0. So if each NP is positive, we call the divisor as effective. So this is not effective divisor because you have a negative sign here, but D2 is effective. So D2 is effective, and precisely because both you have one here and one here, so both of them are positive. So now you can have a partial ordering of the divisor. So one divisor is greater than the other, D2 is greater or equal to 1, if D2 minus D1 is effective. That is, you do coordinate wise subtraction. If you get all positive numbers in the end, you get effective. So that is pretty much it. So you will get something where all integers are positive. So if degree of D is 0, then you denote that subgroup by this. So this is a subgroup. Obviously, degree could be anything. So if say degree is here 2, degree could be negative, degree could be any positive number. But if it is 0, then you write it as this. So this is a subgroup of this bigger group. Divisor is on C. So for a function f in this fraction field of the curve, so this we have defined in algebraic geometry classes. So the divisor of the function is like this. Summation, again, points lie on the curve, NPP. But now NP is the number of zeros. So this NP is greater than 0. You take it as positive if you have number of zeros of the function at point P. Or NP is the number of poles of the function at point P. So if the function has zeros at point P and the number of zeros you count, and you put them as a positive number. If it has a pole at point P, you count the number of poles at point P of the function. So this will be more clear when we see some examples. So D is a principal divisor. It's a principal divisor. You write it as D equals to divisor of f if f is part of this function field of the curve. So to every curve C, you can attach a function field K of C, as we have seen in algebraic geometry. And if the function lies in the functional field, it's called the principal divisor. So what are these functions like? So these functions are of the form f by g, and degree of f is equal to degree of g. So why is this? Because our curve, this is embedded in the space Pn. So the curve is embedded in Pn. So since it is embedded in Pn, both of these polynomials f and g are homogeneous and they have the same degree. So this is because we are working in projective space. So in projective space you deal with homogeneous polynomials. In particular, if you take fractions, they should have the same degree. So therefore principal divisors will have degree 0, because number of zeros of f has to be equal to number of poles given by g, because they have the same degree. So if you factorize them, in particular if you factorize them over complex numbers, you will have same number of factors in the numerator and same number of factors in the denominator, because their degrees are the same. So you have same number of poles and same number of zeros. So then you subtract the number of poles from number of zeros, because you have to add the coefficients up right here. So you will get 0. So if you have principal divisors, your degree is 0. So now you have this relationship. You have divisors on a curve, subgroup of that is divisor 0, and subgroup of that is principal divisors. So notice that we started from here. Divisor 0 formed a subgroup of divisors on the curve. Now we have another portion here, which is the principal divisors. Now we talk about some examples so that these things are clear. So the first example is you have function like this, x by y. So the pole is here and the 0 is here. So 0 is when x is 0, y could be anything, and the pole is precisely when x could be anything but y is 0. So divisor is this. When the function is now this, x by y, x plus y, x minus y. So this x divided by y is precisely this thing. So we copy this portion right here. So you have the zeros and the poles, but now x plus y would be 0 when x is 1 and y is minus 1. You have this, and this will be 0 precisely when x is equal to y. So 1 is to 1. So notice that negative signs correspond to the poles, and these positive signs correspond to the zeros. So another function, now we have y by z, but this is on a curve now. So the curve is y square z minus x cube minus xz square equals to 0. So if you're going to find it on the curve, so for the zeros you have to look at the numerator, and for the poles you have to look at the denominator. For zeros you have y is 0 and you have to see it on this curve. This is 0. For the poles you have to see when z is 0 and then you have this curve is 0. So y is 0, then you have to find the common solution of these two. So just plug in y as 0, and then you can easily calculate that, in first case x is 0, z can take any value. In the second case x is 1 and z takes on the value I, complex number. In the third case x is 1 and z takes on the value negative I. So you can just plug in and see it satisfies. Similarly here z is 0, so you have z is 0, and the only value which satisfies these two equations is 0, 1, 0. So that is y is 1, x is 0 and z is 0. So again these three values are corresponding to x, y and z. So notice again the divisor is, you have your zeros right here, 3 zeros, and you have 1 pole. So notice that this is a principal divisor, 1 minus 1, 0. This is also principal divisor. You have 2 zeros and 2 poles. Now this looks like a principal divisor because we are working in the projective space. So say this curve is embedded in some projective space, say P2. Now this looks like a principal divisor because this is homogeneous, both of them have the same degree. But notice that once you compute the divisor of this function, you have 3 minus 1. So the degree of this function f is 2. So this is not a principal divisor. So this is not a principal divisor. Whereas these are principal divisors, this is also a principal divisor. Although this looks like a principal divisor, but it is not a principal divisor. So that would mean that this y by z does not lie in our function field like this, but you can't see it directly here. So we need some more fine notion to talk about divisors. So better notion is to talk about valuation maps. So we talk about valuation at a point P. So rather than counting the zeros, so notice that our initial definition was number of poles or number of zeros of the function f at the point P. So instead of number of poles, we are talking about valuations. So this should agree. Number of poles and valuation should agree. But this valuation is a more algebraic notion, and it is more subtle notion and a better notion rather than just counting argument. Also, valuation is a ring theoretic argument, so you can ultimately move this on to these sheaves O of t. So our next step now is to define divisors again, but in terms of valuations. And all these examples will still hold in valuations, but these examples are easy to see. You're just counting here. Here you have to again count, but more subtly using valuation of a ring.